Lithium batteries can retain their charges for a long time, but AGM batteries are most happy being flow charged while sitting idle. The charge size solar configuration will flow charge the kicker AGM. The crank charger is designed to flow charge the Promaster chassis starting AGM as well as replenish its parasitic losses in the order of about 100 mA. Two versions of the crank charger are introduced in this video. A third and the best version is being tested and will be covered in the next video. As part of the system requirements, if your Hymer comes with solar, it should really be wired to the charge side or having everything wired to the charge side. Requirement 1. Because the crank charger diverts energy one way from coach battery charging sources to the chassis starting battery to compensate for parasitic drains, it is important to protect the drawdown of the kicker AGM battery. Requirement number 2, we like to have voltages high enough to flow and not just charge the starting battery so that it is always crank ready. Requirement number 3, we like to control the transfer current so that the system will not be overloaded. While lithium batteries can be utilized up to 80% depth of discharge, AGM batteries should not exceed 50%. Still, we assume the worst case if we need to recharge the starting battery from 75% depth of discharge at 12 volt or lower. Our EPEVER solar controller is perfect to satisfy requirement number 1. Using and taking energy from the low port, current transfer will be controlled like an on-off switch at the desired voltage level. The right table shows the parameter set points in the controller for the crank charger application. The general control software is being used in this model of controller with one low port as well as controllers with 2 loaded ports. That is the reason you see load number 1 and load number 2 in the highlighted rows. Anyway, during solar boost charging, the voltage input to the crank charger will be 14 volts and then settle to 13.6 volt. As the sun fades away, the low port voltage will be the same as the kicker AGM voltage. As soon as the kicker drops to 12.8 volt, the low port will be disconnected, keeping the kicker at 100% state of charge. As soon as the sun shines again, the voltage will climb past 13.1 volt, and at that instance, the crank charger will be reconnected and divert energy to the chassis starting battery. The same scenario will take place with shore power. However, the starting battery will not need help by the underhood generator because it will be charged by its own chassis alternator. Here is the first version of the crank charger, good and elegant. In order to satisfy requirements 2 and 3, we need a boost converter with both voltage and current controls. A boost converter steps up the input voltage so that the output is at a higher voltage level. LTC 1871 is amazing that it will never drop out, a must-have feature. That means it will tolerate on and off and all kinds of input voltage fluctuations to deliver the set point output voltage. I leave the other benefits for those who could interpret them. However, the LTC 1871 does not come with current control. It would be nice if we could find a converter that does both voltage and current controls. After reviewing almost 100 converters and playing with a handful, all converters with current control have a shunt resistor connected between the input and output grounds. They will not work because our Hymer common ground by the chassis body will short out the shunt resistor. So we will find another way to do current control to augment the LTC 1871 converter. Here is the block diagram of the most elegant design of the three, which cost about $15 in parts. The solar and the battery ports should be self-explanatory. We use a 5 amp fuse to connect between the positive load port of the solar controller and the positive input of the boost converter. Since the system design can deliver 5 amps to charge a severely drained 9-volt starting battery. A LM338 linear regulator is used to provide current control. The converter output is set to 16.6 volts to satisfy the current regulator voltage differential recommendation. The 20SQ045 Schottky diode is used to block the starting battery, ensuring charging and not discharging. The graph on the upper right corner shows the charge current to starting battery voltage relationship. The blue solid line represents the model before the circuit built. The red dots are the actual measurement point of the hardware. The dotted line is the linear regression fit of the data. There is no charging at nighttime. Daily daytime observations indicate about 0.5 amp average of charging, which puts the starting battery at about 13.1 volt above the 100% state of charge voltage. Here are some pictures of the crank charger assembly. The 3-digit LED flashes the input and output voltage sequentially when power is connected by the solar controller. The LM338 circuitry is mounted on the backside of the boost converter. I messed up the estimation of the heat generation by the LM338 chip. The original heatsink where the chip is mounted seemed not adequate. Instead of using a larger heatsink, I botched it up by adding a same-size heatsink on one side and an aluminum strip on the other side. That seems to work quite well. The blue plastic housing is a $2 shallow electrical outlet box from Lowe's. The crank charger is mounted in front of the solar controller. The positive and negative input wires are connected to the load port of the solar controller. Because of common ground, only the positive output wire is needed to connect to the starting battery. The upper two pictures shows the engagement of the loaded port when the voltage is about 12.8 volts. The solar panels will satisfy the load first at 0.6 amp, and the remaining 0.7 amp goes to the kicker battery. If the kicker were capable of absorbing more current, or the EcoTrack batteries were on, the coach charging current would be higher than 0.7 amp. The lower two pictures shows the disengagement of the load port when the voltage is below 12.8 volts. Charging of the coach batteries and discharging through the load port are controlled independently by the solar controller as shown in the lower right picture of the MT50 monitor. While discharging to the crank battery has been shut off, indicated by the sad phase, a current of 0.6 amp is still flowing into the kicker battery. For those who are interested in the efficiency calculation, charging the starting battery at 12 volt and 13 volt are at 68% and 74% efficiency respectively. Unfortunately, the most elegant design is also the least efficient design. Version 2 is an upgrade based on hindsight from the observed relationship between the charge current and voltage, confirmed by testing. By lowering the output of the boost converter to 14.1 volt and replacing the LM338 regulator circuitry by a 1 ohm current limiting resistor, we arrive at the same charging function but at a higher efficiency, lower cost, and higher reliability design. Here are the conclusions, and I will let you read them yourself. Thank you for watching and have a nice day.